Now, one of the things that I like a lot about science is we're constantly discovering new things, and we're also constantly discovering things that make us question and challenge the theories and the ideas that have come in front of us. One of the biggest challenges out there is the concept called inflation. And that is what this video is all about, is this concept of inflation. One of the questions that a lot of astronomers and physicists have looked at is, why is the background radiation of the universe so incredibly consistent? As the Planck map here, produced in 2013 by the European Space Agency, shows, these color differentiations here are within tiny, tiny fractions of a degree Kelvin. There are slight variations. Those slight variations there are what have led to the variety and diversity that we see within our universe: galaxies, stars, star clusters, etc. So that was incredibly consistent. But the question is, why? Why was the background radiation so incredibly consistent? And traditional Big Bang theory did not have an answer for that. Now, this is the Big Bang theory that's been around for 40, 50 years. They could not explain this, because the idea is, if you would have a normal explosion, in an explosion, it's not going to be consistent everywhere. There are going to be areas where less matter and debris and heat are going to be produced, and areas where you're going to have more heat and more matter and debris. That's just the nature of an explosion. And this was so consistent, so incredibly consistent everywhere, that it left scientists very, very confused. Well, back to one of the greatest living scientists today, Dr. Alan Guth from MIT. And he and his colleagues had an idea. And this idea is the concept of inflation. The universe started out very, very small. And most theories about Big Bang say that it started out very, very small. Now you start quantifying how small is small, and the answer is very small. The big boys probably have a much better grasp of how tiny they're talking about, but something really minute. And what Guth and his team have said is that thermal equilibrium occurred very, very quickly. So that within that tiny little space that was the primordial kernel of the Big Bang, the space was even very, very fast. And that occurred right, boom, right at that little instant of the Big Bang. And then something weird happened. And that is this concept of inflation. Then the universe expanded at an accelerated rate. And that's the only way to mathematically account for this early uniformity. So here the universe was born, and then it expanded to a very big size very, very fast. After it expanded to that huge size very quickly, we do know today the universe is expanding like a balloon blowing up from small to much bigger. But that rate of expansion has been pretty steady through the years. And that's what has been observed. So Guth and his team were trying to account for this original expansion. What they came up with is this: after the Big Bang, this first inflationary period had to be so intense that space itself was expanding faster than the speed of light. Now, I've said many times in this course that the speed of light is the speed limit of the universe. But here is a loophole, if you want to call it that, in physics or in the universe. Nothing can travel faster than the speed of light. That just is the way it is. But that's the speed of light moving through space and time. What Guth and his team have determined is that this original inflation was actually creating space as it went, and all of the rules of nature that we've understand so far say that light cannot travel faster than the speed of light through space-time, but nowhere have we figured out that space itself can't expand faster than the speed of light. So at this unimaginably nutty high rate of speed, the universe went from something as small as a singularity to a huge, expansive version very, very, very quickly. And that expansion happened so fast that the energy was uniformly distributed throughout it. It then stopped that rapid expansion and continued on the normal expansion curves that we have seen for years and years and years. What we don't know what caused this rapid expansion in this first few instants after the Big Bang. Was it dark energy? We need a much better understanding of dark energy before we can do that. Is it an interplay between dark matter and normal matter? Again, we've got to learn an awful lot more about these crazy things, dark energy and dark matter, in order to explain this story of the universe, how this original inflation happened. And I talked about this in the last chapter. After this initial inflation, the universe expanded at a nice steady rate for years and years and years and years. But about 5 billion years ago, about the time our solar system was being produced, what scientists have started discovering is that the rate at which the universe is moving is increasing or speeding up or accelerating. So the universe is again going through some sort of a period of expansion. What's causing that? We don't know. Again, we suspect it has something to do with these two big things that we don't understand yet, dark energy and dark matter. So how will the universe end? We've been talking about its beginnings, but how will it end? As we mentioned in the last chapter, it all depends on the geometry of the universe. How much matter is there? How that matter is distributed. Is the matter open, closed, or flat? The most probable, based on our data at the moment, is that we have a flat universe. One more time, flat universe means it will continue to expand, that rate of expansion will slow, and the universe will eventually stop. How will this actually be? What will occur? It depends upon how much dark matter there is and exactly what the properties of it are. We know some properties, we don't know them all. And the same thing for dark energy. Exactly how much it is, how does it interact? What the heck is dark energy? These two things are big deals in science right now because of the fact that they will help us get better answers to some of these huge questions, like the beginning and the end of time. So what caused the Big Bang? Well, there's a lot of different discussions about what caused that. In order to answer that question, we have to have what is called a better unified field theory. And I'm going to stop right here, and the next lesson I'm going to talk about unified field theory. See you then.